Hi everybody. This is a quick survey of the question from the Heizer Render My OM Lab, problem 3.17b. So this is going to be a quick view of how to set your problem up. And I recommend you use Excel. Open up your Excel. I did a screen grab of the problem and I dropped it in here because I need to copy the numbers that they have here, all this information, into my Excel spreadsheet and figure that out. When we're looking at these time problems, there's three things that we need to do generally. Okay, so the first thing is we need to calculate the expected time through the network for the critical path. So we need to go through all of the activities and figure out what the expected value is using these three times. And then you place them on your network inside the bubbles. Okay, so if this is A, nominal time here would be 9. Okay, so if we were just doing a simple problem and we just use the nominal numbers here, A would get 9. In this more advanced question, we're going to use some probability. If you look at 9 is the nominal number, if you look at the pessimistic number, it's only 1 week. If we're using weeks here, okay, well, let's assume that we're doing weeks because we're talking about new motels or something. Okay, so task A would nominally take 9. Pretty much we're confident that we can get this thing in 9, but we have reason to believe that it could go as long as 10, which is not too bad. It might go over a week. Okay, so pick this problem apart. But on an optimistic note, our optimistic value here is actually 3 weeks earlier. Certain things could align where you might be able to get done in 6 weeks. So there's 3 weeks difference here. Okay. When you look at that, 9 is not centered between 6 and 10. If it were 8, we would be 2 away from 6, we would be 2 away from 10, and this would be centrally located. What we know is that 9 is closer to 10 here. Okay, so this data is not centered around 9, and so we can guess that we're going to pull the time. It's more likely that it's going to be less time than it is going to be more time. Okay, just by inspecting this, the nature of numbers, and when we're doing an average. Well, the first thing that we do is we calculate this expected value, expected time through, for all of these exhaustively. Okay, so the next column over here, we would type in, this is our expected time. And the next column would be the variance here. Okay, so the first thing we're going to do is calculate all the expected times of all these numbers. Okay, and if I start the drawing here, we can see that A, of course, is at the beginning, B depends on A, C depends on A, and D depends on A. So the way that this thing starts setting up, if we start the drawing, I'm going to get you started here, and D. All three of these depend on A, and we need to figure out the expected values through here. Okay, and what you need to do is go through and use these relationships to draw the rest of the network here as to what activity has to happen before the others. So let's calculate the expected value for A. The equation that we're given, and this is a simplification of the broader world of probability, but those in operations, the authorities of operations, have given us a set of equations here. One's for the expected value that we're going to calculate, and the other one is the variance. So the expected value equation is give 1 part A, 4 parts M, and 1 part B, and that's kind of like making pancakes. It's just saying use a little water, use a little eggs, but use a lot of flour. Okay, because basically pancake's going to come out as flour as the major ingredient, and then there's 6 parts in total. So we divide by 6, and that's just a weighted average. Weighted average. Okay, the equation for the variance for any one activity is going to take the worst case scenario, the pessimistic. How far away is that from the optimistic? And we're just told to divide by 6. These are things that you're going to have to know, that you memorize. Okay, and these were massive simplifications of probably more complicated math that underlies this whole principle here. But in industry, we can trust these as dependable shortcuts or dependable simplifications of the problem. That's what we're learning here at PERT. PERT was developed between the government contractors and the contractors themselves. Oh, the government contractors and the government itself on contracts back in the 50s when things were beginning to look bleak, when the contractors were overrunning in cost and time. Okay, so that's what the origins of all this is. And that's why we can depend on them. It's been decades of development here that we can trust this. It's a common language. Okay, just to give you the justification for this. So what's the expected time through A? It's going to be 1 part 6 plus 4 times 9 is 36 plus 1 part 10 all over 6. So we're going to get ourselves 42 here, 52 here. It's going to be 52 over 6. So 6 goes in there 8 2/3. You can do the math, okay? So that's going to be equal to 8.6. All right? And so we see that through probability that the optimistic is 3 away. There's a lot of probability that things are going to happen between 6 and 9 and less between 9 and 10 just because of the spans. And as predicted, I just looked at the numbers and I said 8.6 is something less than 9. So you should get used to the nature of these numbers and know which direction they're going to go, be able to predict it. So the next thing we need to do is go through B and C and D and E and F. And you're going to get all these numbers, these expected variables, the expected times through here. Okay, so you're going to get this whole column of what turns out to be 9, 10, 11, I think 11 numbers. You're going to go to your network that you draw it properly, and within here you're going to put in, these are going to be the numbers to evaluate your network. Okay, so once you get numbers for all of these expected times, then, so the first part is to get these expected values. I'm going to put a big 1 in here somewhere. Okay, so this was part 1. Do all the expected values, do your network, and once you draw your network, you're going to go through here, and the first part is evaluate what the critical path is through all of this. Okay, so everything that we've done so far gives you 11 of these numbers. You just plug them into your network diagram here and do your critical path analysis and figure out what the critical path is through here. Okay, and that's the longest path through here, and what you're going to find out is the expected value of the time through the entire network is your critical path, and they might be these odd numbers like 8.6, etc. All right, so we're no longer necessarily using just the predicted round numbers that we've been using so far. Now we're going to use the critical path, and we're going to add those numbers up. Okay, so we're going to add up. The expected value is going to be the sum of all the expected values along the critical path. So there might be 4, might be 5, might be 6, depending on whatever it is here. You're going to add up the critical path times, and that's going to be your critical path time that you're going to work with. Okay, that's really the first part, all of that. The second part is, as I described, calculate the variance. So the second part is variance. Okay, and what we're going to do is, now that we have the critical path, the variance of the entire network, okay, this is our entire network, through that is going to be the sum of the critical path variances, only the variances along the critical path. So for each of these activities, you're going to calculate an individual variance here. Okay, so we know that's b minus a over 6 squared, so it's going to be 10 minus 6 over 6 squared, and so that's going to be 4/6 squared, or that's going to be 0.66 squared. You got to be careful a little bit in answering online that you use enough precision here, go out enough decimal places when you calculate this. So 0.66 times 0.66 is somewhere around, well, 0.6 times 0.6 would be 0.36. It'd be a little bit larger. I'm not going to do the math here. I can just type it right into one of these cells and calculate it really quickly, but I need you to do that. This is for your gain here. So 0.66 times 0.66 is probably around 0.4. Okay, so I said I wouldn't, but I'm going to go ahead. Let's just figure out what it is. So is equal to 0.66 raised squared, and it's 0.4356. All right, I was just kind of taking a guess there. So we got almost close to 0.5. Okay, so 0.4356, and what is that? That is the variance of A. That's what we just calculated, the variance of A. you only need to do these through the critical path now. So for whatever the rest of the critical path was, calculate these individual variances there, and then the total variance of the entire system is this. Add all those variances up on the critical path. So you're going to get that. Now that you've added those together, you can take the square root of that to get your standard deviation. Okay, so we've just gotten down to the second part. The second part leads us to the standard deviation. Okay, so what's the third part? Now the third part says, once you have how long it takes you to go through this network, and you come up with the expected value of the entire network, what it takes to go through there, let's draw some pictures here. Okay, I encourage you to work with the numbers, and that's how you gain control and become true masters of this. Is what we're saying is, now with 3 time estimates, we have a normally distributed curve of data here, and our expected value is right here. And I don't know what the answer is. I'm not going to calculate the full answer of what the expected value is. That's for the homework. But let's just say, I really don't know. I'm just going to say that it's 21.3 days. Okay? All right? Now, by the nature of numbers, we know that when we have a perfect normal distributed data like this, that half of the data lays below the expected value, half of it lays above the expected value, 50-50. Okay? And this is something as a touch point that I keep driving home here is, excuse me, what's the probability of actually taking up to and including the expected time that we calculated through our project? Well, that only represents 50% chance, all right? So I usually find that should be shocking to people as you start noticing the nature of these numbers. Shocking that now you're more intelligent in this and knowledgeable, that the expected value, okay, the probability up to and including, I'll put a little arrow in here, so the probability of up to and including the expected value is only 50%. I mean, by nature, in risk aversion, as humans, 50% is not a great number. Would you be telling your customer that, yes, we're going to deliver at 21.3 days? That's the whole point here, okay? So the third part that we're working on now comes out as 2 different cases. The first one is, what's the probability of a certain day? Okay, for instance, what's the probability of, we already calculated 21.3, we know that's 50%. If we pick dates beyond 21 days, the probability should go up. Okay, so it's the probability under the curve, we add all of that up, and the area under the curve keeps increasing as we move to the right. So if we said, what's the probability to hit 25 days, at this point I don't know what that is, but I know it's greater than 50%. Okay, so in other words, we know which direction to go here if we're trying to improve our chances. So the first question is, what's the probability on a day that's specific, like 25? Okay, so what's the probability on that? All right, to get through, now with part 3 here, what we're going to do is we're going to figure out these probabilities, and that's where we need the z-tables. Okay, so I gave a longer video about this, but z is just the point of interest. Where are we? What is this point of interest we want? How far away are you from the average? So we have the expected value here. And let's compare it to our yardstick, which is a standard deviation. We arbitrarily decided that that's the average distance to the mean of all the points. Okay, so that's the simple average up here. And then the double average, okay, so the sigma is actually a function of the average distance to the average. So there's 2 averages in there. Just remember that. There's 2 averages. Okay? To mean. Okay, the ADS, average to mean, Control Z. Oh, I don't think it liked that. Average distance to the mean. Okay. Sorry about this is the way the pen works on here. It's not that clear. I'm not too proud of that font that I'm using here. Okay? All right. So what we're doing is we're taking how far are we away from the mean in standard deviations. How many race cars ahead was the winner of the Indianapolis 500? We just arbitrarily picked a car length, and it could be 12.3 car lengths ahead that they won. So we're comparing it to our standard deviation here. So z is equal to this, and it's relatively plug and play. All right. So our point of interest might be 25 minus 21.3. That's our average. And our standard deviation, I'm totally just making this up. You have to calculate it. And the standard deviation of the critical path, remember it's just the critical path, might be 3.2. Okay? So if we did this math really fast, 25 minus 21.3 over 3.2, you have to calculate that. I'm just making this up. And you have to be careful of the precedence of operations here. Use all the parens you need to make sure the things get done in the right order. And if we calculate that, we need to go to the Z table, and it says we're 1.16 standard deviations above the mean. That's what we just calculated here. We're 1.15 or 1.16 above the mean. Okay? And the rest of this, you have to go to your table, and this is your Z table, and most forms of this have increasing Z-scores as you go down the page, and you need to find 1.16 over here and then read in the table a number that's going to be something like 0.7329, okay? And to read that, that's the likelihood, that's a probability number here, and we'll translate it into percent, and it would be 73.29% chance of hitting 25 days. Okay. Now, the other form of the problem says, as a company, let's develop a policy. All right. So let's have a policy, and what we want to do is, with the table, let's say we only want to take, or we will only want to state project completion dates that are 99% likely to happen. So there's not 0.9900 or close to it in our table somewhere, and we work backwards, and we come back and we find out what our Z-score is, okay? And that Z-score should be something on the order, I'm going to guess here, of probably like 32 days, okay? You have to run the data. I'm just giving you the overlay of how you work this, okay? So it might be 32 days, but the way that we work this is we find the 0.99 in the table, we find our Z-score, which would be maybe 3.2 sigma up from the mean, okay? And then once we get 3.2, that's our Z, we just use the same equation, and we have the point of interest. There's x over our point of interest minus 21.3, and we know that our sigma was 3.2, and we just solve for this equation. Okay, so 3.2 is times 3.2. I just multiply both sides by that. This sigma happens to be 3.2 also. Okay, we're solving for this. That is equal to our point of interest minus 21.3. So then we just add 21.3 to both sides, and that is your answer right here if you calculated that out. Now you have to figure out these numbers. But I just ran through the two forms of this problem for you, and so there's three parts to it. So you can review this, speed it up, back it up, do whatever you want with this, but that's the actual setup for this problem. This is probably one of the longer types of math problems, so I think we'll even see in the course here. But once you do this and you get practice at it, you own it. And this skill, you just carry around your calculator and your table here, okay? And there's ways in Excel of calculating all that. But if you use the long form of this, you can use the chart in your book, the reference chart that you have for the Z tables, to calculate that. So I hope this helps, and certainly leave hopefully positive comments or questions below. Thanks.